Welcome to G Fun Facts Online. Today we are going to dismantle one of the most persistent myths in human history. When you picture the Eurasian Steppe, that vast ocean of grass stretching from Hungary to China, what do you see? Most of us see a highway for war. We see the Huns, the Mongols, and the Turks. We see mobile armies trampling civilization under the hooves of their horses, consumers of wealth rather than creators of it. We have been taught to view these nomadic peoples as the barbarians at the gate. But beneath the windswept grasses of Kazakhstan, Uzbekistan, and the Altai Mountains, archaeology is revealing a completely different reality. This was not just a highway for blood, it was a highway for bronze. Long before the Silk Road carried spices and textiles, there was a bronze road, and it carried the most strategic commodity of the ancient world: tin. Today we are talking about steppe metallurgy and the chemical engineering of the Bronze Age. To understand why this is such a revolution in our understanding, we have to look at the material that defined the era. The Bronze Age empires of Mesopotamia, Egypt, and the Mediterranean were built on bronze. It was the metal of their weapons, their tools, and their status symbols. But there is a massive geological problem with bronze. It is an alloy. You need copper, which is fairly common, and you need tin, which is exceptionally rare. For decades, archaeologists faced the tin mystery. The Pharaohs had bronze, and the Mycenaeans had bronze, but they had zero tin in their own backyards. Where did it come from? The answer, illuminated by cutting-edge isotope geochemistry, points directly north to the mobile pastoralists of the steppe. These were not merely herders. They were the chemical engineers of the ancient world, mastering complex redox reactions in pit furnaces and orchestrating an industrial supply chain that spanned continents. Let's get into the chemistry of this revolution. Why tin? Why was this specific metal the oil of the Bronze Age? If you are a warrior or a carpenter in 2000 BCE, pure copper is a terrible material. It is too soft. If you hit a shield with a copper sword, the sword bends. Furthermore, when you try to cast pure copper, it bubbles. It releases gases that leave the metal porous and weak. Early smiths tried to fix this by mixing copper with arsenic to create arsenical bronze. It worked, but it was a trap. The fumes were toxic. It slowly poisoned the smiths, likely giving rise to the ancient myths of lame smith gods like Hephaestus. Tin was the miracle cure. When you add about 10 to 12% tin to copper, you create a supermaterial. First, it changes the thermodynamics. Pure copper melts at 1085 degrees Celsius. That is incredibly hot for a primitive furnace. Adding tin lowers that melting point to roughly 950 degrees. That saves a massive amount of fuel and keeps the metal fluid for longer, allowing it to fill intricate molds. Second, it disrupts the crystal lattice of the copper atoms, making the resulting alloy significantly harder than even iron, though more brittle. And finally, aesthetics. It turns reddish copper into a golden, sun-like metal that projected power and divinity. The problem, as we mentioned, is geology. Tin is found only in specific granite belts. One of the richest of these belts runs right through the mountains of Central Asia, the domain of the Andronovo and Seima-Turbino cultures. These are the heroes of our story. Let's look at the Seima-Turbino phenomenon, dating roughly from 2100 to 1900 BCE. These people are ghosts to archaeologists. They left no settlements, no cities, only graves filled with weapons of unparalleled quality. They originated in the Altai Mountains and swept across the forest steppe with breathtaking speed. Their signature wasn't just metal, it was advanced engineering. They mastered thin-walled casting. While other cultures were pouring metal into clunky stone shapes, the Seima-Turbino engineers mastered lost wax casting centuries before it became common in the West. This technique allowed them to create hollow, lightweight, yet incredibly strong socketed spearheads and axes. Imagine the tactical advantage. A Seima-Turbino warrior could carry more weapons with less weight. Their chemical mastery allowed them to manipulate alloy compositions to ensure the liquid metal flowed perfectly into molds as thin as a few millimeters. While the Seima-Turbino were the mobile innovators, the Andronovo peoples, ruling from roughly 2000 to 1150 BCE, were the industrial heavyweights. We need to stop thinking of them as simple campers. In sites like Semiyarka in northeastern Kazakhstan, archaeologists have uncovered evidence of industrial-scale production. This site covers 140 hectares. It contains a metallurgical district. This was not a household chore, it was a specialized industry. They built sophisticated shaft furnaces. These were chimney-like structures designed to use natural drafts or bellows to drive temperatures past 1100 degrees Celsius. But how did they manage the chemistry? This is where it gets fascinating. The evidence lies in the slag, the glassy waste product of smelting found at sites like Mushistan in Tajikistan. Modern metallurgy separates elements and mixes them pure. The steppe engineers used a more difficult but efficient technique called co-smelting. They identified ores that naturally contained both copper in the form of malachite or azurite and tin in the form of cassiterite. The challenge is that these ores turn to metal at different temperatures and atmospheric conditions. The steppesmiths had to engineer a furnace atmosphere that was reducing enough, meaning high in carbon monoxide, to strip the oxygen from the tin ore, but not so hot that it would vaporize the tin or freeze the copper. They also understood fluxing. They added iron-rich ores or crushed bone to the mix. This lowered the melting point of the waste rock, allowing the liquid slag to separate cleanly from the metal pool. This is advanced chemical engineering. They also had to solve the fuel equation. Producing 1 kilogram of copper required up to 300 kilograms of wood and charcoal. In the treeless steppe, this was a logistical nightmare. The Andronovo solved this by managing woodlands in river valleys and designing their shaft furnaces to act as thermal batteries, insulating the reaction to maximize heat retention. The scale of this industry is mind-blowing, and it is revealed by a shipwreck thousands of miles away. In 1982, divers off the coast of Turkey found the Uluburun shipwreck, which sank around 1320 BCE. It was carrying 10 tons of copper and 1 ton of tin ingots. That is enough to equip an army of 5,000 soldiers. For a long time, scholars thought this tin came from Britain, but a landmark study in 2022 by Wayne Powell used tin isotope analysis to claim that 1/3 of that tin originated from the Mushistan mine in Uzbekistan and Tajikistan. If this is true, it implies a supply chain of staggering complexity. Tin, mined by Andronovo herders in the high Pamir Mountains, was smelted into ingots, traded down to the cities of the Bactria Margiana archaeological complex, moved overland across the Iranian plateau, and loaded onto ships to fuel the wars of the Hittites and Egyptians. Now this is science, so there is debate. Archaeometallurgist Daniel Berger has challenged these findings, suggesting the isotope fingerprints overlap with Cornish tin from Britain. However, the very possibility that Central Asian tin was equipping the armies of the Pharaohs changes our entire view of history. It proves the steppe was not a barrier, but a bridge. We need to rethink our bias. We think technology comes from settled cities, universities, and factories. Steppe metallurgy shows us that high technology, geological prospecting, and industrial mass production can flourish in mobile societies. The herders of the steppe didn't just ride horses. They read the rocks. They engineered furnaces that could breathe fire. They built the Silicon Valley of the Bronze Age on the open plains, connecting the world through a web of metal and fire. That is the invisible empire of the steppe.